let me tell you about the new live transport model that's been implemented at the City of York. I'll begin by giving you some background. I'll tell you about the City of York, its particular circumstances, how they came to decide that a live model would be useful for them. I'll tell you about the live model, how it works, the platform in which that it has been implemented. I'll also go through how the City of York is now using that live model and some of the challenges that we faced in developing the model, and also some closing thoughts and some of the ways that the city is looking forward to using the system in future. Okay, so the City of York is it's pretty old. So we noticed in the name of the presentation we called it the historic City of York, and indeed it was founded in the 1st century. I've got people in the UK in the audience, I see, so they'll probably fact check some of my statements here about the history of York. But it was founded in the 1st century by the Romans, and they called it Eboracum. And that will come up a little bit later in the presentation, you'll see. To the Anglo-Saxons in the 5th century, the city was known as Ephawich, which I think if any of you have been watching The Last Kingdom on Netflix, you'll probably know that already. In the 13th, 14th century, medieval stone walls were built around the city, which largely remain today. And you think I'm trying to advertise a travel to York? I would give it a go. It's a nice place to go. But as well as the old walls, it's also got a couple of rivers running through the city, the Ouse and the Foss. That means lots of bridges in the city, and the bridges and where you can pass through the city walls make for pretty challenging circumstances when it comes to traffic, because they're creating bottlenecks. It's a fairly sizable city in terms of population, around 220,000 people. Due to its historic nature, as well as being a nice place to go, means there's loads of visitors as well, many people visiting the city. And all of these things, mean that, like other cities, but York has its own particular circumstances as well. Traffic congestion is an issue for the City of York, and the challenges that come along with that as well, around emissions and air quality and accessibility and things like that. And so, the city is always looking at ways that they can try and improve that situation. But due to its historic nature, there's not a lot of space, but also there's very valuable things under the ground. So they can't really go digging up the ground as a way of trying to build roads or additional infrastructure to ease the congestion issues. And so it's important that they look to the existing infrastructure, and in particular traffic signals, which are a key tool for the City of York. And how they can maybe innovate with them and optimize with the signals to try and unlock extra capacity. Okay. So there are around 150 signalized intersections or crossings in the City of York. Most of them are vehicle actuated, so that means they're demand dependent. So there's an underlying plan. The signals in the UK are largely stage-based and with interstages, and so there's an underlying plan that the signals are run to, but of course the actual timings that are run change depending on if there's detectors under the roads or cameras looking at the junctions to see where there is demand for those particular approaches. And most of the signals are also connected to the urban traffic centre. So from the control room in the city, they can see what's happening with the signals on the road, and they can intervene where necessary. And with signals being such an important tool to the city, of course, they need to be closely monitored and maintained over time as well. So that the underlying plans that I mentioned that are running within the signals, of course, demand dependent, so they change, but the underlying plans themselves, which, for example, you can see on the left-hand side here, they're regularly reviewed. So they're monitoring the signals over time. They're doing surveys perhaps twice a year to update their models, because they've got digital models of each of their junctions. And so they're updating the flows, updating the timings, and in turn, updating the plans on the ground and in their systems. So there is this regular maintenance process of the plans and the timings that are going on with the signals, perhaps twice a year, something like that. And then also in real time, for the signals that are connected to the UTC from the control room, they have the capability to change things if things aren't going according to plan. Maybe it's not according to typical conditions. Something happens. They can, change the signal plans in real time. They can switch things around. They have that kind of control. But in order to change the signals in real time, to know how they should intervene, of course, they need to have the knowledge of past, how things normally work, but also they need to have a good understanding of the current traffic condition, what is actually happening on the ground at the moment. So if we consider that to be network monitoring, and let's consider how this was done before they had a live model. So in the city, before the live model, in terms of how they know what's happening on the ground at the moment, that's based largely on monitoring CCTV, camera footage, live footage, cameras placed around the city in strategic locations, and also monitoring social media. So by looking at messages that are coming in through Twitter and Facebook and otherwise. So it's by using those things, they can see if there are issues, or they hear that there are issues or things happening on the ground, and then they can maybe look at the right camera and think, okay, this is happening in this particular location, let's change that signal plan. The issue there is that, of course, the coverage across the city is fairly limited, it's patchy. They can't see everything that's happening at the moment. And it's quite reactive. So they can only really react to something once there's already a problem, because that's when it may get reported, or that's when they may see it on the CCTV. And with signals being such an important tool, York have been looking at how they could innovate in this area. They've been looking at that for some time. And one particular source of information and method of innovation that York have been looking at, and goes back to 2016, they've been thinking about how they could use floating vehicle data to improve signal performance. By floating vehicle data, we're talking about data that could be provided by the likes of TomTom or INRIX or others, where they're processing information from, for example, satellite navigation devices in vehicle, or handheld devices, on dashboard devices, or mobile phones, and from another range of sources as well, that tell them what the current speed is on the network in different places. So you can imagine this is quite a useful source of information, particularly when it comes to kind of visibility of what's happening on the network at the moment. So this was identified as a useful source of information to help them with their traffic management. And it led to a project between 2017, 2018, a project called Eberacum, and you may recall that's what the city was named by the Romans. Now in that project, they used live speed data for a particular corridor. It's that one you can see in the top left of the slide here. And they looked at how, with a live pilot project, they could automatically switch signal plans for clearing a corridor. So if on this corridor congestion was seen to be occurring, as identified in the live speed data, then there was a mechanism for automatically switching the signal plans to a kind of plan that would flush the corridor. So by prioritizing green time on that corridor. But it was quite successful, this pilot. It gave good results and led them to consider sort of how could they adopt this kind of technology and innovation across the entire city. And this led to, in 2018, the City of York were awarded almost £3 million for a project called STEP, which stands for the Smarter Travel Evolution Programme. So this being a programme, it consists of various different objectives, but the funding was to cover broadly upgrading infrastructure, which is quite a significant part of the programme. So in particular, making sure that the city's own assets are upgraded digitally and with connectivity, so the information can be fed from what's happening on the ground, and vice versa. It also included investment in a data platform, so a system which can pull together lots of different data sets and process it and provide insights, but also a basis that other systems may be able to use that data platform. But it also provided investment towards a live transport model. There were some other projects involved with STEP as well, such as a live pilot test of GLOSA. But our involvement from PTV, so my particular role in this is project manager from the PTV side. PTV's involvement was to implement the live transport model as part of STEP, and that was together with our project partners, that's Wood and Relative Gap. So, in terms of that live model and the modeling solution, the live model has been implemented using PTV's Optima software platform. So that's this part just here in the slide. And so what Optima is doing, it's receiving live data feeds. So I'll go into a fair bit more detail about how this all works and what the live data feeds are. It's receiving those live data feeds. It's combining that live data with information about typical traffic conditions to create a short-term traffic prediction. So a prediction of what is happening across the city now, and also up to 1 hour ahead. It's providing scenario evaluation, so the capability to test things on this live model, but actually also on maybe what's happening tomorrow or other days in the future. It's generating alerts, so it's capable of being able to monitor what's happening on the network and then alert the network monitoring officers about things that may be happening, that may be different to normal. And it also provides just a nice map of what's happening across the city in the Optima GUI, which is up on a big screen in the City of York's control room. I'll go into more detail about it, but there is also a new strategic model that was developed as part of this project by Wood and Relative Gap using PTV's Visum software. And there is close alignment between the Visum and Optima models, which provides some other additional benefits going forward. As I mentioned before, the wider program of STEP involves also upgrading infrastructure. So we move to the left-hand side. So infrastructure was upgraded to be able to push live data from the sensors that are there on the network. And there's also the data platform, which sits in the middle. And the data platform is collecting this data and communicating with Optima, which is doing the live simulations. Go back to the network monitoring process. So that live prediction, that picture of what's happening now across the city, and the top right is a screenshot from the Optima user interface. So it's the kind of thing that would be up on the wall in the control room in York. This already, that kind of live picture is a big benefit to those network monitoring officers. Because I mentioned that currently they're kind of reactive to finding out what's happening, whether that's by seeing things on a camera or being alerted to something happening through social media or other messaging. But now they have this map, and so they can see visually, they can get alerts about something that may be beginning to build up that's not quite like normal. Then they can be alerted to that and they can react to it. So by having this there, it allows the network monitoring officers to be much more proactive in their network monitoring. And it's also a good basis for implementing the kind of innovations I mentioned earlier, such as using those live traffic conditions to have a much more automated plan switching and being able to squeeze extra capacity out of the network in York. So I suppose the question then is how does it work? How does PTV Optima work for the City of York? Okay, so at its simplest, it's probably this diagram, but I will build this out and explain the different parts of this, and as you'll see. So what Optima is doing is it's taking offline models, talking about offline transport models here, which provide the picture of typical traffic conditions on different particular days. It's combining that with live data. It's actually doing a step first called harmonization. So it's combining the live data and making sense of it to give us a single kind of nice harmonized figure for each part of the network about the traffic condition, combining the live data with the offline models to give a live simulation. That's at its core what Optima is doing. But I'll talk about each of these parts. So for Optima to be able to provide this citywide picture of what's happening, only using a sample from the live detectors of what's actually happening, it needs to know how traffic typically moves through the network. And it gets this from dynamic 24-hour traffic simulations or models, which are developed offline and uploaded to the Optima database, which is in the cloud. Of course, traffic patterns can change day by day, by type of day, by season, by day of the week, and so there's as part of the implementation process, we're clustering similar days into typical days or day types and developing a model for each of these. So for the city of York, we're using just a typical weekday and a typical weekend day for now. And in terms of how to build those models, it sounds like quite a complex thing to have to build from scratch. There are ways to automate it, but for the city of York, we had a really good starting point, which was the new strategic models that I mentioned that were developed by Wood and Relative Gap. So what I'll do is I've got a couple of slides here just to explain what that strategic model is and why it was such a good starting point. Some of you may be familiar with the sort of UK model in practice, especially for strategic models. There are extensive guidelines and best practice for developing strategic models, especially if they're to be used for supporting investment decisions to have a fair and consistent basis. And as part of the STEP modeling project, Wood and Relative Gap, they built a fully UK compliant multimodal strategic transport model using Visum. I did that to a base year of 2019. That's the sort of, I suppose, the starting point for the models that are in Optima. The highway models, as you can see here, they're using a junction-based assignment in Visum, which is called assignment with ICA, but it means that it represents hard capacities, blocking back, flow metering, that kind of thing, within a static assignment sort of context. But it does mean that junctions are coded in detail, as you might be able to just see from the bottom left here. Signal plans are coded in detail, and that is something that we can carry over directly to the live model and its simulations as well. The assignment models are validated to an average weekday in 2019, and the time period based. So it's models for the AM into PM and off-peak time periods. Although not currently used in the live model, the strategic model does also include a timetable-based public transport assignment model, which has a lot of detail, and there may be some scope in future to make use of this in the live model as well. And there really is a lot of data. For example, on the bottom left, you can see sort of how many people are using individual sections of individual services within the timetable. But it's good to have that because it means that from the demand model point of view, it's multimodal, and we've got really good traffic patterns that are feeding into the development of this live model. And the demand model that's coded here in Visum, again, a kind of a UK standard 24-hour demand model, simple tour-based nested logic kind of demand model. All right. So taking that strategic model as a starting point, going back to my previous slide here, we developed these 24-hour dynamic simulations for a typical weekday and a typical weekend day. We calibrated these models, so we began collecting data from all of the live data sources from around October 2020. So we actually used 3 months worth of data between October and December 2020 to calibrate these kind of dynamic models too, using the underlying traffic models from the 2019 model, using tools such as dynamic OD matrix estimation and things like that. As you can see, standard sort of validation tests as we're going through. We'll talk about validation at the end, but we're always making sure as we go along, the models are sufficiently representing the reality that the models are supposed to create. A key output from this process anyway is the demand matrices for these, the amount of demand for these different typical days, and the typical routing, so how the traffic progresses through the network dynamically through time for these typical days. Okay, moving on to the live data then. So I'll give you a summary of the live data that's available for the City of York. So a key input is traffic flow. We need to know what is the current situation in terms of traffic flow, as much of this as possible across the network. So the first thing we've got to do is map all those count locations the city has. You can see a map here on the bottom left. Those are all the count locations in the City of York, which are a combination of loops, or automatic traffic counters loops, but also traffic cameras, which are detecting flow as well. So there's around 100 that will be ready to receive flow. You can see not all of them are currently active, but a good amount of them. So we map those locations onto the network, and yeah, there's around, as I mentioned, 100, and they're pushing hourly PCU flow. So it's just scaling up the count data they just received. It's being pushed to Optima. It's got to be done. So we're talking about latency. This is the amount of time it takes from sensing the traffic flow to Optima receiving information about what that flow is. We've got to have a short latency. That's because the simulations that I'll talk to you about shortly, they're rerun every 5 minutes, and each simulation takes less than 1 minute. So we need that data quickly into Optima system. There's also data coming through to Optima from the signal controllers themselves. So, because the simulation is using the actual signal timings that are happening on the ground. And for that, of course, then it's important for Optima to be sent those live timings. So for roughly 150 controllers, it's capable for, again, York are still working on their infrastructure and their data platform, so more of this data will become available over time. But capable for up to 150 controllers for Optima to be sent the latest cycle that's just completed on the ground, including the interstage timings and the cycle times that will get used in that next Optima simulation. Live speed data is an important input, and for the York project, this comes from TomTom. So information is pulled. In the case of this project, it could be more often than this, but in the case of this project, live speed data is pulled from TomTom every 5 minutes, and you can see roughly the coverage of that in the bottom left here. Yeah, it doesn't cover the entire network that we model for the live speed data. That's okay. It's, you know, the coverage depends on the sample, the amount of vehicles that have been detected in that TomTom feed. But it's pretty decent in the City of York, yeah. So that live data is coming through as well. And then finally, since we're running live simulations, we need to know the current, what that current network situation is, particularly in terms of roadworks, for example. If we're running a simulation now, then we better know if there's a closed road or some signals are turned off or something like that. And so a schedule of roadworks is entered by York in the Optima interface in advance, and they're maintaining that schedule so that the simulation simply looks up in the calendar, okay, which roadworks are in place now, and it will apply them into the current simulations. So expanding out this diagram a little bit now, can see there's actually different routes into Optima for some of this live data. The flows from detectors, whether that's ATCs or traffic cameras, and the live timings from the controllers are coming via the data platform, which I mentioned is a part of the STEP project. That's not something PTV is involved with. There's another company doing that. So the live flows and the live timings come through the data platform. It pushes that information into Optima. The TomTom live speed data is actually coming in via Optima, via a TomTom interface, and the events themselves are entered directly in the Optima interface. So I mentioned that we're recalculating things every 5 minutes, so that there's a whole process of calculations that are on a schedule, I suppose. You can imagine it. Of course, the calculations are shorter than 5 minutes, but the schedule of calculations is rerun every 5 minutes. And the first calculation, the first thing we need to do is to look at all the live data that's been sent into Optima and to run the harmonization process. So this takes the various live feeds. You can imagine you might have flows for different lanes on a single road, or you might have 2 sets of detectors for the same direction on a road that they somehow need to be brought into a single traffic measure. You might have competing sources of information, they're giving slightly different numbers. So all this needs to be cleaned, and we need to provide a single traffic measure, a single ground truth, if you like, of the traffic condition for that road segment. As well as fusing kind of the data and aggregating the data, the harmonization process also cleans, it filters, and it also smooths the data as well. Depending on the project, we sort of adjust the amount of smoothing that may be needed. But just to show a little example of what that might look like, is there's some of the raw detector data at the bottom of this slide. See, it's quite volatile if the data that you're being pushed and captured is over a small period of time, like it is here. And so the harmonization is a sort of moving average, a rolling average of the data, and it's the harmonized data that gets used, the harmonized live data that gets used as an input to the live prediction. And I'll explain roughly how that live prediction works. Okay. So those of you who are strategic modelers, this will look familiar. This is a plot just to help to conceptualize what's happening. This is a plot from the Visum, the strategic model network for the City of York. It's the AM model, but it could be any time period. Remember that we're left-hand drive in the UK. So this is showing that from the live model, from the offline models that we build in advance, we know, for example, this road here, for this location here, we know typically at a particular time of day where people are traveling to. So it could be the green blobs here, if you like. These are the destination zones for people using this road segment at a particular time. And we also know the routes that people typically follow, which, if you like, is these purple lines downstream. So for a particular location, we know from the model downstream of that location how, what people normally do. What you can imagine, and this is conceptual, there's more to it than this, but conceptually, let's say in the typical day models, the flow is 500 here, vehicles per hour. But then the live model is saying, actually, we're detecting, the live detectors say, that flow is 800 here. So in the live simulations, what we can do is we uplift from this point onwards, where we've detected it, the flow to 800, but we can also roll forward that extra traffic through the network along the routes that we know people typically follow. But this is a dynamic simulation, so we also do this dynamically, considering what the network will look like when that traffic gets there, the interactions with the rest of the traffic that's in the baseline model. And because this is a capacity constrained model, you've also got the interaction with the infrastructure. So if this additional traffic that we're loading in at this point creates a bottleneck that wasn't there before, that will be represented in that live simulation. So you might get that you've suddenly got a queue that's created, and now you've got queuing and you've got flow metering in this real-time simulation. But of course, we don't just have one count location in the live model. There's up to 100. You can imagine this gets quite complex when you've got many, many different count locations. But this is what the Optima simulation is doing in real time to give a live prediction of the current traffic conditions, conceptually at least. So what I just explained gives us a live forecast. But actually, there's also something quite useful we can do because we've got these typical models of, like, say tomorrow, what the conditions should typically be all day. We also have a schedule of roadworks and other events and other things that could be tested. You can actually do a near-term forecast and say, okay, tomorrow with the roadworks that are planned, what's the traffic probably going to look like? That's quite useful as well. There are other outputs and other capabilities. So with Optima, people can set up KPIs, and these can be across a whole range of indicators. So, and this will monitor that live forecast or the other simulations, perhaps the near-term forecast, and automatically calculate and record these measures over time. And it could be monitoring a particular corridor, particular link, the whole network, for travel time, for flows, congestion, queuing, all sorts of things. And these can be presented in different ways. So here is the dashboard view. I just grabbed some that I just made up here. Don't necessarily make a lot of sense, but you can see you get nice graphics to see what's happening over the course of the day and what's happening now. Maybe it looks a bit strange now, so maybe that's why we need to react. There's also the map view, of course. So it's showing here. You can set up thresholds. So it could be that you say, if the speed is between a certain bandwidth, it's okay. If the speed drops to a certain level, let's send it orange, and if it goes below another threshold, send it red. And alerts can also be defined on those thresholds. So let's say the speed drops below an acceptable level for a corridor. An alert can be raised, which can be flagged through the GUI, but also could be triggered and sent to external systems, which links back to the use case from the Ibaracum project. Because this is a model-based live prediction, it means that the system can be used for scenario evaluation as well. So, for example, these are some of the use cases that have been identified by York already. So it could be that planning ahead for roadworks, using perhaps what the typical situation will be in a couple of weeks' time when someone requests that they would like to do some roadwork somewhere. Well, that could actually be tested to see what the impact might be, and they can test mitigation plans in advance. Maybe testing signal refurbishment, policy tests such as road closures. Testing, okay, what happens if there is an incident on this key route? What does it look like? And let's come up with a range of plans that we could put into place. And those plans could be tested using this as well. And just an example I've got here is something that we tested as part of the validation of the system, was to say, just here, you probably see where my mouse pointer is. We took a typical weekday, I think this is, and we wanted to say, well, what would happen if there was a closure on this key road? It's the A64 westbound. What would happen if there was a full closure between 8 and 9 a.m. and then while it's being dealt with, there's a capacity drop between 9 and 9:45. And this is just a simulation of what the model is saying will happen, simulating between 8 and 10 a.m. You can see the congestion is building up through time and then gradually easing as the blockage is cleared. So this kind of testing. So in terms of how it's been implemented, Optima is implemented in the cloud for the City of York. It's the users of Optima within the city pretty much at the moment are interacting through the GUI. So there is the Optima interface accessed by the web, by the network monitoring officers. It's up on the big screen, it's on the machines. That provides them with their nowcast, if you like, the forecast of current conditions. Through there, they can do scenario testing, they can see their alerts, and then that is part of their toolkit for being able to intervene in the network, whether that could be switching plans or something. There's also an open API for that for the city, a standard Optima API. So there can also be integration of Optima with all sorts of other systems, like the data platform, but possibly other solutions, such as that automatic plan switching or bus priority or sending public information, that kind of thing. In terms of the quality, I know I've got a transport modelling background, so I'm always asking this question: so there's a forecast, that's fine, but does it actually sufficiently replicate reality? And so how we do this when we're implementing Optima is all the way through, we're making sure the models we're developing are well calibrated, well validated using best practice. Of course, we're innovating. A lot of this is cutting edge, so we're having to decide what that best practice is, but we have a good understanding from previous projects internationally and also from this project. And starting from the strategic models, which are very well built by Wood and Relative Gap, to the dynamic simulations, where we're using typical kind of measures like GH to make sure that the model is sufficiently replicating reality dynamically over time here. So we're looking at also throughout the course of an entire day. We're also, for example, taking a set of data over a few days and storing that and running it through the model as if it was live, so that we can run the model in a lab mode, see what's happening, again compare how it's performing in terms of its simulations. Because you can imagine we're doing a live forecast. Optima is predicting what will happen 15-30 minutes from now, but then that 15-30 minutes from now actually happens, so you can compare how accurate that forecast was. That's what we call the live validation process. And we also undertake realism testing. And in the end, all of this comes together into a validation report, similar to the kind of validation report that we created for a strategic model. So we've done this, and it's been, it was good results, and signed off and accepted by the City of York. That's not to say, it was easy. There are challenges, as with any model, when it comes to validation. And I'd say for live modeling in general, there are particular challenges as well. So data is king. That's certainly the case for these live models. You can't do a live prediction if you don't have live detection and sensing of what's happening on the network at the moment. And for this project, because there are several aspects of STEP that are happening in parallel, we've probably got half of the detectors pushing data, and it'd be great if we could get all of those sensors pushing data, something that the city is working on at the moment. So also the model will only improve over time as those extra data sources become available. It was a challenge to build this model during the pandemic, because you can see on the graph on the right hand side, that's a percentage of an equivalent day or week in Great Britain of traffic. And you can see that throughout 2020, it's dropped at some point down to 30% normal traffic levels, all the way up to where we are now in August, back up to 100%. And our models at the moment are largely calibrated on data through October to December, although we're about to do an update with traffic with data much closer to now. And you can see it was very variable. Indeed, we went through different levels of lockdown during that time. But nevertheless, we have managed to produce a good quality model, certainly with room for improvement. But what York have done as part of their internal quality assurance processes as well is to take the Optima live forecast and compare that to other live traffic data that you can get over the web. You can probably think what I'm talking about, and to assess which one is more accurate by looking at their actual cameras. And we've been told that for all of the comparisons that they made, they felt the Optima forecast was the more accurate one. So it gives us a really good confidence in what the model's doing, Plus we can track that live quality of that live prediction in real time as well. Okay. Good. And so, yeah, I'll summarize, I think. So traffic signals, especially in a city like York, where there's not really any scope for building out new infrastructure. Traffic signals are key, and it's really important for them to sweat those assets, if you like, to make sure they can utilize data and technology to unlock the capacity from their existing physical infrastructure. And what the STEP project set out to do was to upgrade the infrastructure. So, digitally, it's collecting the data. It is out there. It's able to push that live data. That's not as straightforward as you would think. They're also investing in the data platform to be able to handle all of that data, and in the live prediction engine, which was Optima. And what Optima is able to do is provide the visibility of traffic conditions sort of across the whole city, which means that the network monitor officers can be more proactive in their traffic management. An interesting thing that we noticed when working on this project is that it brought together, and to be fair on the City of York, they were already quite closely working together very well, but it's bringing together network monitoring officers, people who are there managing the network every day, with traffic engineers who are there, who are designing signalized intersections, working out what the timing should be, and also transport planners who are typically looking at the bigger picture. It brought everybody together. That was really beneficial. And it's already producing benefits, but it's also a really exciting basis for future innovations. For example, we can integrate buses. In the UK, there's something called Bus Open Data Service. So there's capability, there's potential there to bring in live bus locations, to inform the live predictions and potentially the alerts and how the network is managed, considering bus journey times. Extensions for air quality in real time, automations such as triggering live signal plan changes, freight logistics. So there's so many areas that we can innovate with Optima as the basis. Okay, and that was the end of the presentation.